This is Deep Learning Classics and Trends, a reading group we run weekly. And today we're talking about synthetic data presented by Diganta.
Awesome, thank you. So hi everyone, I am Diganta. I'm a research master's student at Misra in Montreal. Right now I'm at Carnegie Mellon as a visiting scholar. And I'm due to start my PhD later this year at Max Planck in Tübingen. So today I'll be talking briefly about this whole paradigm of using synthetic data and especially utilizing synthetic data in lifelong learning settings. Mostly from a computer vision perspective, but the key takeaways of this presentation is agnostic to modality. So you can most likely also apply the same framework to language or speech or any other modalities that you preferably work in. But before I go into the specifics of my paper, I'll first, we'll do a quick eye test. I like to keep my talks a bit interactive, so we can have like this nice intro into this paradigm of generated data. So we have 3 candidates over here, really cute, Charlie, Foxtrot, and Daisy. So let's just see in the audience who people think are generated out of the 3. You can type the names in the chat. I just want to see where people's perception on generated samples versus real samples looks like. So all of them, all 3, Daisy, all 3. Okay, Charlie and Foxtrot. Interesting. C and D. Okay, that's nice. Yeah, interesting. So quite a lot of all 3s, quite a lot of Charlie. I see Charlie and Foxtrot. Okay, so assuming that people are typing the names of the ones that are generated and not the ones that are real. But to people who typed all 3, they're incorrect. There is in fact one real dog in here, and that's Foxtrot. Now, to people who got that correct, I mean, fantastic. But the point being here that we are coming to a point in time where it's becoming really hard to distinguish between real samples and generator samples. And more surprisingly enough, the Charlie and Daisy samples that you see over here are generator samples are not coming from like a really state-of-the-art generator. This is just Stable Diffusion XL Lightning. So, I mean, Stable Diffusion 3 has come out. There's more stronger on-paper generators, which arguably can provide more photorealistic images. And the prompts that I use to get these are not also something detailed. It's just a photorealistic image of a dog in a field and a photorealistic image of a Samoyed in the snow. So there's nothing really detailed about it, but you can see the point being that generative images have become really, really undistinguishable from real actual samples. So I just got this quote from this wise old model that everybody uses, ChatGPT. It said to me that, you know, data is wealth and generated data is basically its exponential growth, which I completely fairly agree with. Because we know that like all of our models are based on the foundational premise that we want to model the real world scenarios, the real world phenomena, the environments that human beings operate in, and that is modeled through basically data that we collect from everyday scenario, and that can be in different modalities, different form of precisions can be acquired through different sensors. So data is becoming definitely the most important paradigm into scaling models that can be practically applicable for all economically viable tasks. And we have seen that with foundation models, especially being trained on humongous amounts of web scrape data. So definitely, I know that people also put a lot of emphasis on the architecture aspect of deep learning and how we can scale them, but it, I think, is in conjunction with how we scale data and especially the quality of the data that we acquire. Surya Ganguly had a really good paper on data pruning and how to beat the conventional power laws of data scaling with like more efficient ways of data pruning, and that basically serves as the foundation for this quote precisely. So in vision, at least, we have come a long way. Basically, if people have read the original Eigenfaces paper, we've come a long way from that regime where now we have generative models which can generate really accurate, photorealistic, true to attribute images of human faces, and not just human faces, but also compositions of different characteristics, attributes, concepts, scenarios, which just wasn't possible earlier on with the generators that we had maybe a decade ago. And obviously, deep learning timelines are very much accelerated these days. Even 1 year feels a bit old now. So definitely 2014 is probably in the history books. But yeah, so the point being that generative data is definitely picking up pace and at a rapid growth. And we see that in a lot of generative models these days. We can now generate concepts that you won't even see in natural world. You won't see an animated fox in a cinema hall eating popcorn. That just won't be possible. But these models have the capacity to model the representations, the attributes of these concepts, and gel them together in a very naturalistic way. If you were an artist and you were asked to sketch up a painting of a fox having popcorn in a cinema hall, you would probably come up with something very similar to the images that you see in the slide, which is quite a marvelous sight to see of how far we have come in the generative AI landscape. And this is not just me trying to sell this to you, but we all know that all of this driving force in generative AI is coming from a lot of companies and big players in the market betting huge on this technology. So there's like Google, there is OpenAI, Runway, Apple, Meta, Pika, Stability. We all have heard of these household names, and these are obviously more prominent names in the space. There are obviously more and more startups who are tailoring these generative models towards very specific business applications like ad design or fashion design or movie creation. So definitely the usability of these generated samples or generative scenes is becoming more and more prominent, with also the rise in quality of the generator samples we can get. I have a very close friend from Barcelona who's actually a movie director. And they recently used, I think, Midjourney and Stable Diffusion for a fully productionized short length movie completely made out of generative scenes. So it's really incredible to see that happening these days, which just wasn't possible earlier. So I want to base this talk in the premise of moving from supervised training to the paradigm of generative supervised training. So essentially relying on data that is sampled from a generator. And in this case, the generator can be a text to image generator, it can be a video generator, it can be any form of generative model in any modality that is concerned for the problem. Before I go into the specific work, I want to give a bit of literature reviews. So recently there have been a lot of works that have tried to explore this problem, which is to try augmenting our real data sets that exist that people use for benchmarking or training with generator samples. And people have shown that at ImageNet scale. There was a paper from Google where they showed that they fine-tuned a diffusion model exclusively for ImageNet synthesizing, and then they coupled real images and generated images and showed that most of the models like ResNet-based or transformer-based that you train on just ImageNet, now when you train on real plus generated versions of ImageNet, you'll probably get a stronger performance boost, not only in the in-distribution or in-domain setting, but also in out-of-distribution settings as well. And intuitively, it makes sense because we have seen previously works on augmentation, and we know how powerful augmentation is. Everybody has used some form of augmentation in some image classification training-based pipeline, either that may be mix-up, cut mix, cut out. Obviously, they have more theoretical implications in how they affect the training process, but the idea being the same, that you want to synthesize samples that can augment the space of samples that you're presenting in the training data set. And there has been also a paper from Meta where they tried to diversify the sample generation process by creating more contextual diversified prompts and style diversified prompts, and then using a frozen diffusion model to synthesize new images that you can use for training. And not just in naive image classification settings, but people have also tried this in multitask settings where you can generate task-specific images. I won't go into the specifics of this work, but what I want to basically highlight is that synthetic data's importance in training process is not only limited to just like ImageNet classification settings, and also not in the space of image only modality, but there has been works also going beyond image modality to pure clip training using synthetic data. So there was a paper recently called SynthClip, which trains end-to-end a clip model. I'm sure people are familiar with the clip model from OpenAI. It's just a standard contrastive language image pre-training model. And they trained it fully end-to-end on synthetic captions and synthetic images generated via those captions from a text-to-image model. And this basically gives a really strong confirmation on how we can utilize generator data, not only in image settings, but going to multimodal settings. There has been also work where people have tried using the same motivation towards synthetic audio-based training. I'm not super familiar with the research in audio modality. So this is a paper from 2021 that I found. So I'm pretty sure there has been works since 2021 that I've also utilized synthetic audio and training audio foundation models. If people have good references, please feel free to share it. But the foundation being here that synthetic data has been used in audio and also has been used in reinforcement learning problems. So definitely we see that the horizon of usability of synthetic data is ever expanding as we make these generators more and more powerful. But we are in a timeline where scaling is sort of one of the biggest let's say, question concerning any deep learning problem. Does this problem scale? Does this model scale? Can we get better performance out of it? And can we predict the scaling behavior as well using scaling laws? So you can beg the question that, oh, you have shown me settings where generated data looks good, works good in ImageNet, but I think ImageNet these days has become CFAR. So mostly people don't really put a lot of weight onto ImageNet performance, at least in the classical settings. So definitely people want to show that the performance scales beyond ImageNet to more realistic setting. And there was a work last year from Philip Isola from MIT and the group on whether utilizing generated data can keep giving positive reward in terms of improvement in performance as you keep scaling it up. And the answer is not as nuanced as saying yes or no. So the paper basically claims it is not really the case, but I would put a small asterisk beside that statement. And the reason for that is there is a lot of variability and arguments that you have to take into assumptions when generating data from a generator. You have to take into consideration the prompts you used, you have to take into consideration the style vector that you used. And if you're using stable diffusion, then you have a lot of hyperparameters like guidance scale or the number of sampling steps. So it's definitely not a one-off answer that you can give. And most of these papers that I showed you recently where you use generated samples, they only rely on one generator for the training process, which means they generate from one text-to-image generator with the exact same settings, and usually with a fixed set of prompts, and then show the performance return you get on scaling the sampling from that one generator, which is all good and fine. But in the subsequent slides, I'll show you from our paper how we motivate that using one generator alone is suboptimal, essentially. So you should instead utilize an ensemble of generators. And we all know from classical machine learning settings how ensembles can help in improving performance, and it is no different in generative processes as well. With that in mind, I'll just briefly pause here if there's any question before I go into the exact paper. So I'll just quickly open the chat. None as of now, but yeah, feel free to interrupt me if there's any questions in between. Okay, so in this presentation, I want to discuss primarily about my work that I did in collaboration with folks from Yonsei University and Carnegie Mellon on the paper titled, just say the name, Online Continual Learning with Category Names Only via Data Generation. The preprint is available already on arXiv, so if people want to check it out after the talk, feel free to. So let me give a background of what this paper is based on. So I gave you a good foundation, I hope, on the usability of generated data, but why, as a researcher, should you care about generated data? I think everybody who has taken ML 101, DL 101 has probably trained on the famous IRIS dataset, the famous MNIST dataset, CIFAR-10 datasets. These all datasets broadly fall into the category of manually annotated datasets. Basically, that means that the data sets have images coupled with their labels or ground truth labels, as you call it. So because you use it in a supervised training setup, you essentially, the loss would be basically comparable to the label that you generate from the network to the ground truth label that you're provided from the data set. Now, these are really good data sets, no questions with that. But manually annotated data sets by default come with a lot of issues at hand. For example, they are not controllable. You only have the images that you are provided in the data set at hand. Sure, you can augment them using spatial augmentations. I'm specifically only talking about image data sets in these cases. So you can augment them through mix-up, you can augment them through cutout, cut mix, or any other spatial affine transformation augmentation as well. But technically, you cannot get more images out of it, which represent the same concept, but in diverse settings. So you have a finite number of samples. You have storage issues, yes, because you're expected to download this data set, have it locally, wherever you're training it on the server and the cluster, or locally if you're training it on your local device. Ideally, it doesn't come with usage restrictions. If it does come with a usage restriction, it is written clearly in the dataset metadata in terms of what it can be used for and what it cannot be used for. And usually, these manually annotated datasets that we use are not containing private data. I understand that this is not the broad scope of all datasets available, but think of it in the most natural and general settings. You would not expect private datasets available to the.
Yeah, so just a quick question. Where do you draw the boundary of controllability here? Because the generated data will ultimately come from manually annotated, right? So this was an issue, for example, with Google when they had the image generation, and that came from a data set that was set to be a certain demographics, etc. So when people were using that to generate images, ultimately came from a manually annotated data set, right? So in terms of controllability, you didn't have much control there. So again, how do you delineate the boundaries here?
So I've heard this argument that, like it's all going back in a circle because generative models are also trained on manually annotated sets. So usually they will model the distribution that they experience in the manually annotated sets. When I say controllability, you can't see compositions in manually annotated set, which you can generate from a generative model. Which you ideally won't see in either because the manually annotated set is long-tailed, or either because it just doesn't have enough examples of a particular concept in combination with another concept. So that is one way to define controllability. And the second way to define controllability is just the pure Oracle setting, where ideally you would expect that a very strong generator can just instead of modeling the exact distribution, memorizing the exact training samples that it has seen from the manual annotator side, it can actually understand what the concept represents and just keep generating it in very diverse settings. So, and Husky in a very arbitrary setting that you wouldn't see in a manually annotated set or wouldn't find a real image of. So I think that is where I would sort of put the line in terms of controllability between manually annotated and generated set. Does that make sense?
Yeah.
So
can I ask you a question? So
yes,
the source of your training is always annotated images. Is it correct?
The source of what? Sorry, I couldn't hear that.
Of your training, of the training set.
In case of manually annotated sets, yes.
And the purpose is to generate synthetic images or both? text and annotation and images?
So in case of generated images, the annotation you provide it as a prompt, right? So if you want to train a cat versus a dog classifier, your labels are cat and dog, then you can just prompt the model to give you n images of cats and n images of dogs, right? So you wouldn't have to explicitly label images generated from a model like this is a cat or this is a dog. Does that make sense, like the differentiation?
So you create a model which with the ability to generate synthetic images. Is it correct?
We don't create a model. I mean, there are already available text-to-image generative models that are available pre-trained, so we just utilize it, which is a standard. Like there are like several. There is DALL-E, there is Stable Diffusion. They all can generate images given a particular prompt about a particular concept.
So then, I'm sorry, probably I missed it somehow. So what is the main purpose of your research, if possible? Could you?
Oh, I haven't gone there yet. That is coming in the next slide. So I'll talk about what we did in a while. This is just the motivation of what we are trying to do. All right. So, yeah. So with manually annotated dataset, you can have high acquisition cost. If people have read some of the collection processes of manually annotated datasets, especially in the VQA dataset, they had to use mechanical workers from Amazon Mechanical Turk, which obviously costs dollars to obtain. And subsequently, if you look at the opposite end of the spectrum, which is web scraping, which is most of the current foundation models have relied on, you have the huge Lion 5B dataset. They have some controllability, but again, you can't obtain all possible type of images of all concepts and all possible compositions from purely web scraping. And they have a lot of noise. For example, like we typed like dog in Google search, and some of the images are of hot dogs. So they're not necessarily the exact same semantics. Even if they have the word dog in it, that doesn't mean that it represents the same exact concept. So there can be different types of noise, watermarks, copyright protection, license protection. You might encounter private data from web scraping. And some of these have been highlighted by data provenance institutes and mechanisms that have tried to understand the data sets that people are using as a byproduct of web scraping them. So definitely there is issues on that front as well, even though it is a rather cheaper alternative to obtaining really large scale data that represents the natural world. And then there is generated data, which sort of offers a nice leeway that doesn't rely on most of these issues that confound manually annotated and web scraping. So you usually can control it. You can generate images across diverse concepts, composition of diverse concepts in different styles, different scenes, and usually don't have storage issues. You can just store the model and impromptu sample as many samples as you require at whatever instance of time whenever you're training. So you don't need to explicitly store data. And obviously, when I say that there is no user restriction and no privacy issues, that is somewhat not true. I mean, people have shown that diffusion models do memorize the training data and can leak private sensitive information. But I'm purely talking from an Oracle perspective over here, that in an ideal setting, if we train the model with no private data, and the generators especially, and no data that have any user restrictions, then yeah, in an ideal world, we wouldn't experience samples generated from it, which would have those issues. And this is what I was saying, right? If you purely web scrape with some of the class names from some data sets and obtain images by pure web scraping without any filtering, then you will see some images which truly don't resemble the exact same concept that you want to be present in your training data set. So as you can see here, for the concept house, it generated a clip art of a man holding a keychain with the symbol of a house in it. Maybe it is useful for training for the concept of house. We do not think so. And then when we write horse, it gives us an engine. There's schematic diagram of an engine, because engines have this metric of horsepower. So that's where the term horse comes from. So definitely the instances of noisy images that you can encounter by naive web scraping if you don't do any filtering. So there's definitely issues with web scraping, which is what we want to highlight. So that was the first part where I wanted to motivate why web scraping and manually annotated data sets are not necessarily the most optimal way to obtain your data to train your model. But the next thing I also want to motivate is that we should also look towards training these models beyond static settings to more continual settings. We train models these days, foundation models, on millions and billions of dollars, and there are huge computational resources required to train these models. But training a static model comes with consequences. It decreases the shelf life of the model because, for example, take Copilot, for instance. I believe everybody uses GitHub Copilot here. Copilot, if it is static trained, it wouldn't see or experience data of new package versions or libraries that will pop up beyond the training window that it has been trained on. So if you prompt it to generate code which is specific to PyTorch 2.x and it never saw 2.x in its training, then ideally the model would not be reliable for getting code in that specific version. So we want to train models continually with the dynamic nature of our world and how the environment shifts, how new data arrives every point of time. Every day people upload thousands and thousands or millions of images on the internet. So there's definitely not a lack of abundance of data, but rather the nature of the models that we train, which is more restricted and static in nature, which decreases the overall shelf life of these models. So our work is based on this paper that came out last year from Meta and Oxford and KAUST, where they basically construct this framework of doing continual learning with only names or categories. Here, names means just the concept name, like the class name, like dogs, cats, or whatever the classes names are in the data set, without having any access to the actual data, and then utilizing web scraping to be able to do so, to train the model on web scrape data. So more precisely, this is the framework that they propose. So at every task, they basically see different concepts or different classes like cats, dogs, bears, and ducks. And at every task, they basically prompt 4 different image web search engines, Google, Bing, DuckDuckGo, and Flickr, obtain the web scraped images for those corresponding classes, and then just train a linear probe. So you can see over here, F is the model, which is frozen. So they only train this linear probe for those 2 corresponding classes at every task. And then when they go to the next setting, they again receive more data for the new classes or the new concepts that they see in that task, and then correspondingly increase the linear probe size to accommodate those new classes. So this is good. This is a nice framework. However, in this case, as you can see, they only train a linear probe and not the full model. So the full models remains end-to-end frozen, except the linear probe. And there's not explicit continual learning mechanism going on over here. And as I highlighted before, that there are issues with web scraping. So it's not the most optimal way to obtain your data for training continual learning models on if you want to have more clean and diverse data. So I think that was sort of the background. Now I'll go to the specifics of our work. So remember I told you before that most of the papers that have utilized generators for generating training samples to train the models on, they've usually relied on a single generative model to generate all the required samples from. But this is where I sort of draw the differentiation. That is suboptimal, and the more optimal way is to utilize an ensemble of generators. Now, why that is the case? So here I basically show the example of where I use 2 different prompts for the same concept. The concept is highlighted within the bracket, which is person. And I generate samples from 4 different text-to-image generative models, DALL-E 2, DeepFluid, IF, SDXL, and CogView 2. You can see that the semantics or the style and the variations in images provided for the same concept and the same prompt is quite different for these models. Like if you look at the first prompt, which is a black and white image of person highlighting dramatic contrast, DeepFluid IF gives me images which are more portrait in nature, focused on the face of the person. It does have dramatic contrast in it, but it's very monotonous in terms of the style of the images that it generates. But you look at SDXL in contrast, you can see that the variation is a bit more vivid. You have a lady standing in front of a window, so very different posture as well, and very different style representation. it also abides by the prompt, yes, but it does generate images which are perceptually significantly different than what Deep Flood IF has to offer. And this is the main thing, that we want to take the strengths of these models, because these models have been trained with different data, different training protocols, different compute budget. So they obviously have different knowledge representation of these concepts and will ideally generate different samples when given the same prompt and the same concept. So with that, we basically formulate our framework, which we call Generative Name Only Continual Learning, or abbreviated as G-NoCL. And the framework is outlined as this. So you have K tasks. This can be a lifelong setting where you keep receiving new tasks. A new task here is conceptualized as just new concepts. And these concepts can be anything as simple as labels. So just the name of the classes like dogs, cats, or it can be more descriptive like metadata or attributes of a concept. So the framework is not necessarily constrained to just label names, but can be anything which describes a particular concept. What we do is, as we receive these concepts over time at every task, we basically have this Psi module, which essentially constructs a set of diverse rewritten prompts by iteratively passing the base prompt through Gemini. Now, I clearly understand Gemini is probably not the fan favorite model. People would prefer sometimes ChatGPT to be used. We'll come to the point of why we use Gemini in our process. We have some qualitative results against GPT 3.5. We didn't try GPT-4. But the process being that we take the concepts in as they're provided, the label names, the attributes, or whatever that might be, and then we construct these prompt rewrites, which is a set of diverse prompts that we are going to use to generate the samples from the generators. Now, the reason we don't use only one prompt, the base prompt, is because it offers limited diversity. It doesn't encompass the different settings or different scenes or different compositions that particular concept can be seen in natural world. So we ideally want to have more diverse prompts that can give a wider scope of that particular concept from a natural world perspective. And then we pass these prompts or use these prompts to sample from a set of generators, in this case, DALI 2, SDXL, CogView, and Deep Flood. But we can sample naively, right? We can sample 100 images from each of these generators and call it a day, but we don't do that. So we have a data budget. So to abide by the data budget, we have an ensembling function represented as delta here. This ensembling function is basically a sample complexity guided measure, which we use to weigh each generator's contribution to the ensemble for the particular concept. I'll get into specifics of how we do that exactly in the next few slides. But the idea is we then subsample from all of the generated images that the generators provide, construct our training data set, and then generate our model, in a continual learning fashion. So we do have continual learning mechanisms like experience replay, dark experience replay, or LiDAR that we use to train the model on the generated samples.
Quick question, what exactly is the delta, what exactly is that doing?
Yeah, I will get to that. So basically what, before I get into specific, what it is doing is, let's say you generate 100 images from each generator. You have 400 images, but your data budget based on whatever your budget is let's say 100. So you now have a decision to make is which generator will provide how many samples, right? You can obviously take arbitrarily equal uniform contribution from each generator, but we say that is not the best approach. So we basically have a sample complexity guidance that we use to measure the contribution of each generator.
Something you're training, or
no, we don't train it. It's zero shot. So I'll explain the exact measure in the next few slides, but there's no training involved in that process.
Got it. Thank you.
So what I want to stress over here, that this framework, we design it in a way that it is general enough, which means that you can ideally swap out components here. So if you feel that our prompt diversification module is not the most optimal and you have a better idea, then you can simply swap out Psi and replace it with your own prompt diversification module that would benefit your particular setting. And similarly goes for the data filtering process that we have with Delta. You can also swap that out with your data filtering process. So I wouldn't claim that this is the framework and has to be like this, but this is at least what we tried in our work. So I'll just pause over here. I think there's some stuff in the chat on the generative. Yes, but they are assuming the model is trained on a large enough to learn the overall controls have been determined. Yes, that is correct. But generative model, okay, I don't think there's any specific question. I'll address these comments at the end of the talk, but yeah, let's keep moving. I didn't get how he obtains the meta prompt. I'll get to that specifically in the next few slides. So basically, the way we do the prompt refinement or prompt refiner module is, so we have the concept, let's say in this case, dog, right? That's the label name. And what we do is we wrap that in a base prompt. And the base prompt in this case is the simple clip-like prompt. This is an image of the concept name. So this is an image of a dog. That is the base prompt. Then we simply ask Gemini to provide diverse meta prompts constructed as rewritten versions of that base prompt. So I haven't highlighted the specifics of that in the slides, but you can refer to the appendix in the paper where we show how we do that. But it's simple. It's like just a zero-shot prompting to Gemini saying, okay, this is my base prompt. Just provide me a set of diverse meta prompts that encompasses this concept represented in the base prompt. So we generate 10 of those meta prompts, and then we simply ask Gemini again to rewrite each of those 10 meta prompts in 5 different ways. So just like synonymous rewriting. So this might sound somewhat familiar to you if you have read the paper about language rewrites, where they trained a clip model by rewriting the captions of CC3M. So they basically prompt ChatGPT with the original caption for that image and just ask it to rewrite it. And then they use the rewritten version provided by ChatGPT to train the clip model. So we use the same procedure to basically rewrite our set of 10 meta prompts, each in 5 different ways. So we end up with a list of 50 prompt rewrites.
Is that
now what
choice
yes,
between the meta prompt and the rewrites dictated by the context size? Or because you could just have generated 50 meta prompts, right?
Yes, we could have. We just like early on during the project when we asked like it to generate a lot of different meta prompts, we saw a lot of duplication. So when we deducted the size of the meta prompts through manual inspection, the ones that looked unique decreased. So we wanted to constrain that and then rewrite all of them. That makes sense.
So that way you're ensuring that you have more variety in the rewrites then. Okay.
Yeah. Okay, so and then we, as I said, relied on Gemini, right, instead of utilizing, and as I said, we only compared to GPT 3.5. So what we did is the set of 50 prompt rewrites that we obtained, we basically computed the cosine similarity of the pair embeddings that we obtained through a sentence transformer. So each column over here represents a sentence transformer from Hugging Face. I'm pretty sure people are familiar with at least sentence T5 and Lapse. So we just computed the embedding and then the cosine similarity between each of the pairs of the prompts that we generated. And we saw that Gemini, on average, has lower cosine similarity. That basically means that the prompts generated are more diverse, at least through this metric. But I agree that this metric might not be a foolproof indication of that, but this is what we relied on to suggest why we use Gemini. But we obviously did manual inspection as well. And we found that Gemini, on paper, at least compared to GPT 3.5, was resulting in more diverse prompts. So again, going back to the importance of having the prompt rewrites and not just relying on meta prompts as was asked a minute ago. So you can see over here, we have 2 meta prompts. These are all images through Stable Diffusion XL only. So the meta prompts are a photo of the concept being person in earth tones, and then a vintage photograph of person with a warm faded aesthetic. It generates certain images of certain characteristics and attributes. But then when we rewrite that exact same prompt, so all of those prompts over here in the first top row are just rewritten prompt rewrites that we obtained through Gemini of this original meta prompt. And you can see now when we prompt these rewritten versions of the prompt, of the meta prompt to the same model, we get different aesthetics and different style and different attributes of, for the same particular concept. So essentially diversifying our image data set. So that is the end goal that we want. We want our image data set to be as diverse as possible, encompassing different scenes and different color profile and different palettes. And that is the same case for the second meta prompt as well. So I hope I have convinced you on the use case and the motivation of why we did this two-step process rather than relying on just the meta prompts.
Another quick question related
Yes.
to the meta prompt is there a way you sort of filter out meta prompts that are just outlandish and probably not going to be useful for, because it could just, say, a person riding a space, whatever, I don't know, rocket in space or something, right?
Yes, we did that through manual inspection. We unfortunately weren't very quote unquote nerdy about having an actual function or a code that can filter them out. Yes, there were prompts that were a bit outlandish, but not just outlandish, but also multi-concept. So we are only considering a single concept setting over here. So single object classification, not multi-object classification. So there were times where it generated meta prompts of two different concepts paired together. We ideally don't want that. So we explicitly filtered them out, but by hand, not through an actual code. But I think that's a fair criticism of our work, that we can only do so much manually. So it is something that we are working on to improve.
Thanks for that.
Can I ask a question?
Yes,
So
please.
the meta prompt is already generated by a model, by Gemini, right? So the
Yes.
photo person. So before that base prompt, maybe it's just a photo of a person, or is it?
Yes. Yeah. So that is just the clip-based prompt, which is a photo of the concept name.
So the earth tone, like all the things vintage, are added by the model.
Yes.
You prompt the model to say that, please write a meta prompt of this concept.
No, we don't say it as meta prompt. We say just rewrite this concept in diverse setting with diverse color profiles and palettes. That is basically what we ask. That is why it more over focused on the style attributes and not different settings. So most of the meta prompts that you'll see will be specific to the color profile. It will be analogous colors, neutral colors, earth tones, or vintage style, or minimalistic representation. So mostly stylistic representation is what we obtain in our meta prompts.
So the same concept person, if you write 5 meta prompts, you would be would be earth tones, the other might be totally different. Some other tones are
exactly.
Each of them is rewritten into 5.
Yeah. So I show over here 3 of them, but yeah, for each of the meta prompts, we have 5 rewritten versions of it.
See.
Yeah.
In the chat, there's a question about seeds. You use the same seed.
Guess but it's hard to keep the seed across different engines. Otherwise, if you like a resampling of the same prompt. Yes, this is a good question, because obviously we also have different generators, so it's hard to keep them synchronous. Like we are generating from Stable Diffusion XL, from CogView, from DALI. So you can argue that it can be just a resampling of the same prompt, but we generated enough images to see a consistent difference between generating with only the meta prompts and the prompt rewrites. So actually right now, before this talk, I was generating only with the meta prompts and the base prompts more than 5,000 images for the same concept, just to show the diversity in the style. It's not there in the paper yet, but we'll update that. So you'll probably see that the consistency in the stylistic representation that we get only through the meta prompts is somewhat distinctively different than what we obtained through the prompt rewrite. So to some extent, you can argue it's resampling, but also we can say that it's actually doing something significantly different. But it's hard to pinpoint that, to be honest. Okay. So now I finally want to talk about the sample complexity guidance as a measure that we used to filter out the samples in our ensemble. So here's the interesting part. So I probably sold the idea that we should rely on different generators for different concepts, for different use cases. And this comes from a very interesting perspective of sample complexity. So last year, there was a paper at NeurIPS which had this formulation of the Mahalanobis distance. So if you come from out of distribution background, you might have heard of this metric quite often. So they have this metric called relative Mahalanobis distance that basically they use as a measure for sample complexity. And what we did is we simply evaluated the same concept, the prompts from different generators, and just saw what kind of sample complexity score defined by the RMD we obtained from these generators. As you can see in the right-hand plot over here, for different concepts with the same prompt, on average, we see that not the sample complexity on average doesn't follow the same profile across the generators. So in this case, the RMD score, the higher it is, the more complex the sample is. The lower it is, the more easier the sample is per se. So as you can see in the right-hand plot, for the concept of eyeglasses, you can see Stable Diffusion XL on average has higher RMD score. But when you go to the concept of candle, then Deep Floyd IF has higher RMD score for its generated samples, at least the generated samples that we obtained through our process of generation. So given this motivation, we also qualitatively saw some of these examples. So maybe I'll motivate you from that perspective. So when you see the concept of guitar over here, this is a generated example which has a low RMD score. You can see the guitar is at the center of the image, very much uniform color profile. There's hardly any disturbance or artifact or noise coming from the background. But when you go to high RMD versions of generated examples for the same concept, you'll see that it's quite different. And so you have a different view perspective and geometry of the same particular object, which is a guitar over here. When you go to the class of giraffe, you can see there is more like interference from the background. You have more elements in the background as compared to the more uniform color profile that the low RMD example follows. And same goes for elephant class. You have different textures, more richer textures than what you obtain in the low RMD example.
So how are you getting the relative Mahalanobis distance here? You get the sample and then calculate the RMD for each image. Is that what you're doing?
Yeah, I have the exact formulation in 2 slides, I think. Here, yeah, I'll get here in a while. So I'll talk about the exact formulation. Okay, but for now, just assume that low RMD is easier examples, high RMD is more complex examples. But I'll get to the exact interpretation of the metric. So it's not just concept-wise. So like these generators, they don't differ in the average RMD of the generated samples in terms of different concepts, but they also differ when it comes to prompts. So some prompts for the same concept will generate images of different average complexity as compared to others. So if you see over here, the prompt of a vintage photograph of concept with a warm faded aesthetic has average RMD score of 2.4 as compared to something like a minimalistic image of concept using clean lines and muted colors, which has a lower average RMD score. So natively speaking, some of these concepts, when wrapped with a specific type of prompt, will generate more complex samples as defined by RMD as compared to other. And this is just a visual overview of the same. So here on the top row, you see low RMD basically prompts that on average provide examples or generate samples which are of low RMD as compared to higher RMD ones. So you can see maybe the most distinctive one is the elephant class. The textures are much more vivid. You can see from the house, there is more background interference. There's more trees covering the house. For the dog image, you have the obstruction of the field. But when you see the low RMD examples, are very clean, the less obstruction, less artifacts, very focused on the concept. So what is this metric and how do we utilize it? So we utilize it based on a probabilistic measure that we call DISCOBER. So what is RMD? Basically, RMD is nothing but the distance of the sample from its class-wise prototype and the global prototype, the difference between the two. So we use a clip visual feature extractor to obtain the features for the targeted sample, and then all the class samples, and obtain the class centroid, and then the global prototype being all samples generated prototype. So we just obtain the difference between the two distances, and that is what the RMD score encapsulates. But this is not our formulation. This is what the NeurIPS paper used, and we just utilize the same exact formulation to motivate why we should rely on different generators. And hence we construct a probabilistic measure called DISCOBER, which basically gives higher preference to generators for concepts where we have average higher sample complexity. So if Stable Diffusion XL, for example, has on average higher sample complexity for the generator samples of the concept candle, then most of the examples that we accumulate for the concept candle will be contributed by Stable Diffusion. And vice versa, we give lower preference to samples of generators which have on average lower RMD scores. So, but it's a non-zero probability. So we still have samples of low RMD in our ensemble set, but yeah, higher preference is given to those which have on average higher RMD.
Is that based on results you were seeing? Because to me, it sort of makes sense to have more of a balance between the vanilla ones and the more artifacty generators.
Yeah, so exactly, that is literally in this slide. So I'll talk about why we do this. So we basically compare. So as I said, DISCOBER is the method that I talked about in the previous slide, which gives higher probability or preference to more complex samples and lower to lower complex samples. So let's see what are the other possible options. So none, or the baseline, is where you don't have a set of generators. So you only have stable diffusion, and you generate your whole data budget from stable diffusion using the rewritten prompts. Then you have equal weight ensemble, which means you have the 4 generators and you give equal preference for each concept to each of the generators that you have. Then you have K highest RMD ensemble, which means instead of doing this probabilistic interpretation where you give higher probability to high RMD and lower probability to low RMD, K highest just will take the top K sliced example set which have the highest RMD. So it will never take into consideration the lower RMD examples. K lowest is literally the reverse of it. And inverse probability is basically the inverse of DISCOBER, which is giving higher preference to lower RMD examples and lower preference to higher RMD examples. So at least you can see in this setting, we have evaluation on both in distribution and out of distribution setting. The metrics over here, because it's an online continual learning framework, we have area under the accuracy curve, and A last is the accuracy at the completion of training. The method that we propose, the data selection criteria that we propose, has the best quote unquote performance that we obtain. So you can see it doesn't give that much benefit over K highest, but it's still a non-trivial improvement. So does that answer your question?
Yeah, it does. It does.
Okay. So you can actually interpret this from a sort of a SVM perspective as well. So think of it in this way. You have the sample manifold where you have 2 classes represented as orange balls and purple polygons, and you have the class center represented as darker patches of the same classes. Now, if you only picked lower RMD examples, they'll be more concentrated around the class prototype. When you try to learn a classifier, the degrees of freedom that you have, that you can express to separate or linearly separate these 2 classes, is much higher, because I can draw a line in n arbitrary ways to partition these 2 classes, at least from the training version. So the less highlighted ones are just those that are not included in the training set. But now if I take high RMD examples along with low RMD examples, high RMD examples will be more farther away from the class prototype, but consequently so they will be more closer to examples of another class. So it gives a more tighter boundary for the classifier to construct to linearly separate these 2 classes. So consider these high RMD examples to be nothing but support vectors for the classifier, if you're familiar from the SVM perspective. So
isn't there also the caveat that because you're generating, you could just have wonky artifacts in the high RMD cases as well?
Say that again. Sorry, I didn't get that.
Because you're generating, right? These are not natural images. You could have wonky artifacts in the high RMD examples as well, right? So that's the reason you want to still have the low RMD, because that's still covering the core concepts, right?
Exactly. So the reason why we include low RMD but with a lower probability is still because the mean, or the class centered, is just the mean representation of the class, right? It encompasses the most meaningful way, and you can arbitrarily represent that particular concept. So we still want to maintain that in a classifier, but at the same point, we want to ensure that the classifier is exposed to more diverse scenarios or settings or scenes or styles where that concept can also be encountered, which is the potential.
I wonder because you're doing the high RMD training, I wonder if that actually helps with the adversarial robustness as well, implicitly. You doing that? I know. Yeah,
it can possibly. I mean, we do OOD evaluation, which does show significant improvement. So maybe that is somewhat of an indication that it might also help in adversarial setting. At least we haven't tried it, but that's definitely a good suggestion. We'd be happy to discuss further if you want to try it yourself, or we will also try it probably in our settings as well.
Oh, sorry, go ahead.
You have a question, sorry?
I'll just wait till the end.
Thanks. Okay, so results wise, so basically the settings that we tried, because it's an online continual learning framework, we have 4 data sets: PACS, domain net, CIFAR10W, and CCT. In this case, we have a differentiation between the ID domain and the OD domain. So ID is most usually the photo or the realistic domain, and the OD domain is the more stylistic different versions. So like art, cartoons, sketches, clip arts. And then for each of them, we have different task partitions and different number of classes and different number of classes per task. This is a gigantic table. I'm sorry about how cluttered it is, but basically what this table represents is these methods over here are continual learning methods. Their aim is to prevent catastrophic forgetting, which is one of the primary goals in continual learning. So these are just standard methods that are available off the box from any continual learning library that you can use. And then we have different baselines. So we have the web scrape data, which is following the same earlier Oxford paper that our paper is based on. So scraping from 4 different search engines, then filtering from that to the data budget. Base prompt is basically the original prompt, the first prompt, no meta prompt, no rewriting. So generating all images only from Stable Diffusion XL using the base prompt. Then diversified prompt is utilizing the prompt rewrites, but also only generating from Stable Diffusion XL alone. And then GenEnsemble or generative ensemble is our method, so which is the discover plus diversified prompts. And then we have the manually annotated data set for each of these data sets that we used in simulation. So we definitely do outperform web scraping in most settings, if not all, especially in OOD, the margin is superior. In fact, we also outperform manually annotated data set in the OOD evaluation. We necessarily do not outperform in distribution evaluation against manually annotated, because the manually annotated data sets are constructed such that when you train on it, you'll get good performance on the ID test set that is provided by the data set. So we consider it as sort of an upper bound. But you can see that there's clear benefit of utilizing this generative ensemble or discover method in general for as compared to at least web scraping or utilizing single generator with single prompt settings. This is with ResNet 18, but the results also hold in case of Vision Transformer and also in case of CIFAR10W, which is a quite competitive data set, OD set of CIFAR10. Lastly, I want to show the scaling behavior. So when we increase the size of the data budget or the ensemble size, so we have a fixed data budget, as I said before, which adheres to the total data budget data that we have in the manually annotated set. But if we kept scaling this using the same discover method, then we do see a nice linear power law trend that the ID and the OD performance keeps increasing as you increase the generative ensemble set size. It's definitely not y equals to x linear, but it does show positive improvement as you keep increasing. But sure, it can bottleneck at some point, but we only went up until 4x the total size. Yeah, okay, so that is it. I hope I covered everything and I'm on time, but thanks everyone for listening in. If there's any questions, I'm happy to take it right now.
Yeah, I had a question. Just going back to the intuition of choosing these sort of harder samples, you have this like decision boundary graphic motivating it. I'm curious to know if you've like when you visualize the high R&D or quote unquote the examples in a class that's close to other classes or quote unquote close to the decision boundary, if any of them are like, or if many of them are kind of like just bad examples. And what I mean is like, you might imagine instead of, you know, kind of selecting this, you might instead generate, for example, these kind of harder examples by saying, generate a dog that also looks like a cat. Or you might say like, you know, take a dog, take a cat image, and then just like linearly combine them or something. So I'm wondering like if these actual generated sort of images from the image generators that are hard to classify are better than just some kind of like noisy image, if that makes sense, right?
That makes sense. So we do clip filtering where we see that the class is consistent. So we also like saw the images that were generated by the high RMD examples as shown by some of the qualitative examples I showed showed you over here. So they're not deviating necessarily from the specific class that you prompted or concept you prompted the model with. So we didn't see of any particular example where quote unquote, even though we give the interpretation that it is closer to samples of another class, that it is actually showcasing any attributes of another class. So that we haven't seen, at least with the examples. So this interpretation is just purely an interpretation. It's not supported by like actually seeing the data manifold or something like. We don't constructively plot this figure from actually the samples generated. This is just to provide an intuition on why this might be working out. So to answer the question of whether it's noisy in the sense that there might be some linear combination of the features of another class, yeah, we don't see that, at least with the high RMD examples through manual inspection. Does that answer your question, or were you asking something else?
Oh, no, that answers my question. Thank you.
Okay.
So this is more of a comment about the conceptual underpinnings of using synthetic data generally. But, generative models, they're learning an approximation of the underlying distribution, right?
Yes.
And so ultimately, it's going to be hard for them to go beyond that approximation.
Yes.
For an individual model, right?
Sure.
And so I see that like using multiple representations with the meta prompts allows you to explore the space of that model's approximation more thoroughly, right?
Sure.
But you eventually you can't really go beyond the model's approximation of the true distribution. And
yes.
So I'm just wondering how you think about that issue.
Yeah, no, I fully agree with that argument. I think like this is something that I pointed out a bit earlier, right? Like at the end of the day, all of these generators are trained on data that is available, and ideally they are trained in a way that they model that data itself. But the thing is, like for some of the concepts, we won't see composition of that concept with specific attributes in the natural world, which we can generate from a generator. For instance, if you were to type like a husky in a specific, doing a specific action in a specific setting, you probably might be lucky to get maybe 2 or 3 images, or maybe 5 or 10 images out of that specific prompt from web search engines. But if you ask a generator, you'd probably be able to sample way more diverse scope of that same exact action in that same setting, because these models are trained such that they can compose different attributes and different concepts together, which you just won't see in the natural world. And also, as I said, yeah, sorry, go ahead.
But I mean, you're interpolating in the space of the approximation.
Yes.
Right.
So yeah, I mean, we don't argue that we can generate something which is beyond what they have been trained on, or what the concepts that they have seen. So we also argue all of the concepts that we'll see over each task, the generative model has been exposed to those concepts or those attributes. So at no point we say that, okay, we are providing a concept that the generative model hasn't been trained on, because we don't have any training to either the prompt rewriting process or the generative model. So they are all zero-shot frozen. We just sample from it. So yes, that is a fair assumption that we have to take with the construct that these generative models are trained on. But I think that's just the way it is with how we have these generative models available to us and their capabilities. So yeah, our work doesn't go beyond that scope, at least unfortunately with this one.
Cool. Yeah, no, thank you.
I also had just a comment, but I guess going back to the initial step for like prompt writing, one thing I am curious about is like how much these sort of, let's say, diversity of data really depends on this syntactical rewriting versus kind of having like different attributes. To make that clear, one thing I'd be curious to know is if you, instead of, asking Gemini or some large language model to rewrite it multiple times, if instead you say, okay, like as a human, I kind of know intuitively what sort of diversity I want. So like maybe you want diversity in one attribute, let's say color, or another attribute, I guess you have like earth tones or some kind of like, I don't know. I'm just wondering, like, I'd be curious to know if you just take like your meta prompt and kind of like, if you have, that's like a list of different like colors, or like a list of different, attributes for a different attribute. And then you essentially just literally do like a for loop. You do like all permutations of all the sort of like types of attributes that you designed beforehand, right?
Mhm.
Because it seems like, at least when I was looking at the prompts, these sort of attributes are kind of universal to any object,
Mhm.
right? Like
Yes.
describe it in black and white, describe it in earth tones, like it seems kind of
Yes.
universal. So I'm wondering like if there really would even be a benefit to essentially having this kind of large language model rewrite it versus just like injecting knowledge of like, this is what I want diversity on. These are the attributes
Yes.
in which I want to have diversity on. And that way you can even have like, I guess you could have the quote unquote like, uniform, you know, like I guess like expressivity or diversity versus worrying about or like having the concern of like these rewrites kind of be like converging to one thing and not getting diversity, if that makes sense.
Yeah, no, absolutely, that makes sense. So I think like one of the papers that I highlighted does something similar. So this right figure that you see over here, it's from a paper that I came across after we submitted our preprint. So this does somewhat similar, which takes into consideration contextual diversification. So has different attributes which you can compose together with the specific concept, in this case the object. So first they have this module where they generate the attributes of the concept. So what attributes define a crane, for instance, it's a large long-legged bird, and then rewrite that in through a LLM where you define other attributes where you might just see that concept, like you might see crane in a marshland or you might see crane in a water bodies. So they do this. We unfortunately did not, but yes, what we want to try in our follow-up work is to have provided the concept-wise attributes, so not make it universal prompts for every class names, but have for each class the specific attributes and compose with different variations of those attributes, which I hypothesize that would significantly improve not only the prompt rewriting process, but also the generation process. So definitely, that's a very strong, plausible improvement that we can do on our framework. So yeah, I completely agree with that.
I have a different thought there. I feel like
Yes.
your meta prompt is trying to capture diversity. It's trying to generate the same concept with different tones, different angles.
Yes.
Your rewriting is less about diversity, but more about crafting a prompt that's familiar to models. Because when we write it, we might not write it in a way that the models can best use it. Language models accept some kind of prompts better. Like starts with
Yes.
something photo.
Yes.
Those techniques
Right.
are not quite mastering yet, but a model itself might rewrite it to a region that's more familiar with.
Right. So initially during this project, we had the idea of having a feedback loop from the generative process back to the prompt rewriting process, such that we, during the end-to-end training process on the fly, update the prompts such that it reflects better in the generative process. But because we are in an online continual learning setting and the compute constraints is such that it becomes a bit infeasible to have that feedback loop unless you relax some of those constraints. So that is why we don't have that. But ideally, yes, you can have a feedback such that the prompt rewriting process is guided by the generation. But right now, when we rewrite it, the rewriting module doesn't have any explicit knowledge of what the rewritten prompts will be subsequently used for. So it's not necessarily quote unquote generating rewrites which are more favorable towards generation, but just rewriting to ensure that it has semantic consistency with the meta prompts, but it is different enough that it will result in different generative samples.
Yeah, for sure. It probably wouldn't rewrite in a way that directly optimizes the end result, but because it's generated by a model, I feel like it's using the model's language instead of our language.
Absolutely. I mean, yeah, we took a look at it. I definitely wouldn't have come up with some of the rewrites that it, if I were asked to do so, and maybe the average human also wouldn't. But yeah, that's like open for interpretation and speculation. So yeah, definitely, plausibly, that can be going on.
I know we're super over, but quick question. I was wondering about, again, the diversification, because you showed examples that made it clear that, yeah, for individual samples, it's very hard for us to tell whether something was made by model or not to some extent now. But in distribution, a lot of times we can, but it's harder to measure if we can or not. I have some experience with like generators happening to generate much more a part of the distribution than the rest of the distribution. For people, this is important where you have bias, where it generates, like, for example, StyleGAN mostly makes white people. And then how do you account for that? How do you know that your diversification is actually providing what you want in distribution when there are no real measures of this, or like ways to look at it in one image and say, yeah, that looks like a good image? Are there rigorous ways, or is it kind of like you
No, I think that's
eyeball
a
it in
fair,
distribution?
yeah, that's more like eyeballing, I would say, because yeah, that's like completely fair. I've had this similar experience where we have seen like from different generators some specific attributes, especially for human face generation process, like blonde females are better paired with eyeglass attributes, so you would see less images of males with eyeglasses. Yeah, that's definitely a case with at least how these models have trained, the distribution that they have seen during training. For the data sets that we have, we don't have such a fine-grained nature of concepts that we will encounter such detailed bias towards a specific attribute. Most of these concepts that we see in these data sets are very like superset level of concepts, like just dogs or just cats or person. So it's not like very specific, quote unquote, like dark-haired man, for instance. We wouldn't see that, at least with the setting. But yeah, if we were to extrapolate it to fine-grained classification, or not even fine-grained, but multi-concept or multi-attribute settings where you want to have two attributes together, I can see it can be a problem. But yeah, like as I said, this work is sort of the first work in the direction that we want to build on top of. So there's definitely room for improvement. And one of it is to have a more rigorous measure of quantifying the generation quality process.